Okay, so this week at Paper Club, Vahan is going to be presenting a paper about self-supervised learning. So it's very recent, it's from ICLR this year, and it shows it introduces some very interesting concepts, which they call self-distillation. So yeah, please, Vahan, go ahead.
Thanks, Carlos. Actually, this one is from ICML, but yeah, very new. I chose this because it was this paper because it's a combination of a few interesting concepts. Well, so self-supervised learning, interesting augmentations for input data, but also self-distillation, another interesting concept that relates to ensemble learning. So it's a bit of a mix of different techniques, and I hope we can have a good discussion during the presentation. I actually took a few notes for myself to discuss further because I didn't fully understand a few things here. Hopefully we can do it together. Okay, I'll share my screen. Should be here. Cool. All right, so let's start with the introductions. I'll just start with this graph here because the paper is about self-supervised learning, which is applied on data sets that actually have labels. So normally, self-supervised learning is used when you don't have labels or you don't have enough labels. And the idea is quite straight, the classical idea, straightforward, which is take a data set, train two models. One is to train for labels. The other one, just like you can see here, is to train on augmented data. So for example, for images, you would rotate the images, or you would flip the color schemes, as you can see in the image here. So RGB would become RBG and so on, right? So you just rotate the colors. And then you train two models, but so that they share the same parameters. And then you would use this training of two models to do inference, right? But the authors of this paper decided to ask a question, which is, can we use self-supervised techniques to improve performance on labeled data sets? Okay, think of it as advanced step from data augmentation to improve generalization, right? They cover it later, but to mention briefly, if you are training a model, it is a common practice to augment the data. Again, same things, rotate or change color schemes, or if there are a few other augmentations you can do, which is meant to improve generalization, model generalization. It's kind of a regularization technique. So they thought, can we do this self-supervised learning in a way that it can improve training models on labeled data? Well, if you do it the standard way, as we will see later, the performance actually drops a lot. If you just use the normal, what they call multitask learning self-supervised models, then the performance on fully labeled data sets will drop significantly compared to just normal training. So to solve that problem, they start with investigation. I'll scroll down a bit here to show the plots. We'll go back to the formulas in a moment. They start with an investigation how data augmentation affects no, let's rewind a bit. The data augmentation is used the following way. You start with you assume there is a data transformation, for example, rotation, and your model is trying to learn the transformation, right? So they start by observing how much the data changes if you apply the transformations. So here in this experiment up here in figure 2, we are comparing MNIST of images from MNIST. For example, you have 1 versus 9, right? And then you compare rotations. Okay, so we can see here that 1 versus 9 rotations seems to, this is the TSNE, these are the TSNE plots, seems to keep 1s and 9s quite separate, right? So 1s are here, there is very little mix. But if you rotate 4s and 9s, they start getting mixed up, which means they are much harder to learn from, right? Because the optimizer may not be able to tell the difference between 4 and 9. And they use this experiment to demonstrate why multitask learning can actually decrease the performance of training fully labeled data sets. Okay. All right. So this was a quick jump to get some more motivation why we are looking at these methods. Okay. Next, let's look at some building blocks. Okay, we are going to look at, we are going to build a loss function that will suit our purposes. Okay, so let's first look at what will happen if we want to use the classical self-supervised multitask learning on fully labeled data sets. So they call it MT, which is multitask learning. Well, not multitask because there are actually 2 cross entropy losses. One of them is for normal labels. The other one is to learn transformations. In our case, rotations and color scheme transformations. Okay, and then well, they also mention here that there is the data augmentation loss, which is basically just the part with data augmentations, right? Just the first part. Okay, so that will be the data augmentation loss. So to build a classifier that doesn't suffer from rotation invariance problems, which we saw before on the MNIST examples, can harm the optimizer to actually minimize the loss function. They propose a relatively simple change, which is instead of having 2 functions, two loss functions, sum of 2 loss functions, basically build a cross entropy loss using joint probability distributions. So if you look up here, right, so that's basically softmax from the joint labels. Okay, and then they just propose to minimize that. So it is important to note here that I'll scroll up and show that even though we are changing the model, we are not increasing the number of parameters, but we are increasing the number of labels, right? Because now our labels become cat, no rotation, cat, 1 rotation, and then dog, the same rotation. So we get all possible permutations here. Okay, so each label is.
It's not quite right. The omega W's or omegas, they are added, right? They are trained as the model is learning.
Yes. So you mean here? We can look at the part B, right? So there is an aggregation part here at the end. Is it what you are saying, Arvid?
There's in softmax. There's the W, right?
Mm-hmm. Yep.
And that is trained, right?
Yes, they're trained together.
Yeah. So there is slightly more parameter that is explored.
Yes, slightly more. Yes, I should. Because for example, they say for is it for Cypher 100? There is 0.4%.
Yeah, they do argue.
More.
Yeah, they do argue that it's negligible, the amount of parameters that I think it's for ResNet 32. They add 0.4% more parameters.
Yeah. Just 0.4%, which is, they argue, is negligible. Yeah.
Sure.
Good point. Thanks. Yep. I actually didn't get to aggregation yet. I was still talking about the labels, but yes, thank you. Yes. So after this, having these labels, there is a second step. Actually, there are two more steps. First one is aggregation, which we'll get down here. Yeah, that's the sum here, right? This is what you are saying, Arvid, the sum of cross entropies.
The W is already before the aggregation step, technically, right? Because it's already in the SLA term.
Yeah. W, yes. Yes. Yeah. Sorry. Yes. Cool. And then we have to do a few more steps for inference, because inference can aggregation for inference, right? Because this is also softmax, but at inference time we already know the transformation, which means we don't need to do the transformation, but we only need to consider only that the original labels, which we can find out here, but then there is a problem with inference, because then we have to do end up getting inference for as many inferences as transformations, and then we aggregate them, which is why when they propose what's called self-distillation. So normally distillation is between two models, right? But here they're proposed two separate models. But here they're proposing to do distillation between for the same model. It's kind of like ensembles. So you would kind of like ensemble training. You would get inference for each transformation, and then get the logits. Actually, I should scroll up to the here. So you would when you get to not have to do the aggregation at inference time, we will add the term for our loss function also during training time to combine the logits, which is just before the softmax, with the aggregation result, right here. So that's the self-distillation part. So we are basically using multiple outputs from the same model combined with itself, and end up with a model that so that at inference time we get only one inference instead of all of these. Okay, that's just to speed up the inference. Let's look at the loss function there, which is down here. So self-supervised label augmentation loss, which is the original loss we had, and then we have this KL divergence from the aggregated probabilities, which is defined right up here in 4. So that's the softmax again. And then there is an extra regularization bit. So I'm not entirely clear why not the regularization, extra summand here, extra cross entropy, but I didn't really get why they add the third part with hyperparameter. Does anyone have any ideas why there is the last bit? No?
I was just thinking. So the second term essentially is training a separate model that tries to predict what the aggregation would have said otherwise, right?
Mm-hmm. Yeah.
And the last term is making sure that this term still gives a correct prediction, right? Because otherwise the aggregation itself would not necessarily be normalized and stuff. I'm really not sure about that.
Yeah, I was a bit weird too, because, well, this aggregation part, I thought this this is the self distillation, right? Because you have the logits here, which is what it is, right?
Yeah.
But the last bit, they don't really motivate it either.
So,
they just
and
say
sigma was the output of the distillation module.
Yeah, so the last term is the distillation term. So at inference, you will only use the distilled classifier. So you have
So
to train the distilled classifier as well.
So
Yeah.
you mean, which is why beta is 0 or 1. So the training time is 1. No, training time is 1. And then why is it 0 or 1? I say it's a so hyperparameter 0 or 1. So they sometimes use it, sometimes they don't.
I don't know.
Yeah, I hadn't noticed that.
In the SLA term, is there the SLA term also knows about the different transformations, right?
I think
so SLA is defined.
they use the hyperparameter for the ablation study. No?
Not sure.
Okay, maybe we'll see in the ablation study experiment. Yeah, I wasn't sure about this, and I thought maybe we can figure it out.
Yeah, because for sure the third term is the distillation term, so that's the one that trains the distilled classifier.
Isn't it the second one? The second one that makes sure that the predictions of the average of the aggregation and the prediction of the sigma, which approximates that, are similar? I would have thought that is the distillation part.
That's what I thought too. That's what the second term is.
Yeah.
Because when they say beta is a hyperparameter 0 or 1, it's not a range, right? It's 0 or 1. That means they choose to use it or not use it.
Yeah. In principle, it shouldn't be necessary, right? In principle, the SLA term should make it so that each transformation aggregate becomes good, right? And then P aggregated should be good, and then of course sigma trained to be like P aggregated should also be good. But for some reason they short circuit this information flow.
Should we search for beta and see where they gave it values?
Yeah.
No, it's not used any. They don't mention it anywhere. So
hi there.
Hello.
So I was just thinking that distillation's different from ensembling, because we're trying to compress kind of the knowledge of a deeper model or a more information-rich model into a simple one. And is it too naive to think that maybe since it's self-distillation, the beta 01 there is just a switch to actually determine if it can be distilled down into a simpler classifier?
So sometimes you want to switch it off. You mean?
Yeah, maybe you just can't. Maybe you just can't switch. Yeah, maybe you just can't distill the more complicated model down in the sense, and so you get a better fit by just not doing it. To make the discrimination, you actually have to have the more complex model available.
So if you don't use this distillation, then at inference time, you still need to aggregate inferences from multiple results.
It's a thought.
It's either that, or because they don't want to have to compute all the transformations, so this set transformed, when you are training the distilled classifier, you only turn it on for the non-transformed examples.
Okay. Yeah.
So you have sort of two trainings going on at the same time, right? You have the one with all the transformations, and then you have the beta. Oh, but it's a hyperparameter.
And why would you train on non-transformed samples? I thought that was the whole point, that you transform them so you have more stuff to predict on.
Okay, should we look at the experiments, and then maybe we realize based on what experiments they run. So they talk a bit more about implementation. So they try to use any available code they found, a few more, and then they also mention, they use the HGD with momentum for training, fixed batch size, but they also use smaller batch size for if there are not enough training samples, right? So I guess standard things here. So transformations, as I said, they use only rotation and color permutations, but they didn't use an interesting transformation technique, which, let me find it, a puzzle. What's it called? I can't find the name, but they mentioned that they didn't use that puzzle
The jigsaw puzzle
transformation
approach.
Jigsaw puzzle, yeah, which is a bit weird. Like basically they do squares and then they make the model learn how to reshuffle squares to reconstruct the image. It doesn't seem to make a lot of sense because how does it help? Because how does the model know its neighbors? But anyway, they didn't use it, which is, I guess, makes things a bit more simple. But they did use both RGB channel swapping and rotation. So they end up with, well, 6 times 4, I guess, but they actually used only 12 transformations. So you can do all possible combinations and get even more transformations. Right, so small toy study to understand data augmentations. Well, we talked about this briefly, so I guess that's okay, because they experiment with MNIST to see how transformations make the optimization problem harder. And then they run a few more experiments. What they call a baseline is the standard model, which is some sort of I think it's a ResNet, but actually depending on the problem, there is a standard model, and then they do additions on it, right? So the SLA model plus self-distillation. They also compare with ensembles. Naturally, ensembles perform better than the baselines, but they also use ensembles. No, self-distillation only goes with ensembles. Well, needless to say, performance improves with this method. But I wouldn't focus too much on how much performance improvement we get. Even though there is improvement, it's just I found this paper quite interesting because of the different techniques they use, and also a little bit confusing with all the annotations. Like every time you have to think what each annotation means. Right. So the second experiment is looking at data augmentation and multitask learning comparisons, which is given in figure 3, which is here. So iterations is basically batch updates. Okay, so that's not epochs. I think it's just batch updates. And then they show how accuracy changes. Well, training and test accuracy. So dashed lines are test accuracies, and they have 3 different models. SLA only with data augmentation, and on the standard multitask learning self-supervised model. You can see that they kind of follow same curves, and then there is a jump here because they adjust the learning rate. 40,000 iterations, they half the learning rate, I think. So the performance jumps for all, but actually, interestingly, only data augmentation training curve is the highest, but not the test one, which makes sense because what we are doing is really improving generalization, right? The test curve remains highest for SLA. Cool. And then, of course, comparison with ensembles. Kind of saw the performance gains here with ensembles. It's important to note that they said that inference takes the same time for all models, right? So they use the self-distilled models, because otherwise it's not fair. If your inference takes 12 times more time, it's not a fair comparison, but they made sure it does. And then there is an experiment comparing permutations, right? So baseline, well, normal model, and then performance gains for each permutation, and our models, which are self-distilled model and what's AG? Augmentation? No.
Is it aggregation?
Aggregation, yes. Thank you. So there is no, is there no self-distillation then?
Presumably so.
Yeah, self-distillation is only during training, then they deploy the distilled model. That's why they can have several models have the same inference time.
Yeah, true. Thank you, Carlos. Yeah. So one thing I found a bit confusing is the performance gain is relative percentage. So there's not percentage point gains, right? That's like relative percentage. Which we should pay attention to. I guess evaluation of standard setting. So that's comparing several different data sets. So until now, experiments were showing how each component of our method contributes to the learning process, right? And now we are going to look at several data sets and different methods, okay? And see how much relative gain each of these methods brings to the baseline model. So these numbers are relative gains for relative classification error rates compared to the baseline model. And so they propose a few different methods here. So the SLA plus SD, and then they show that their method can be applied to other methods, right? So in addition to, I actually don't know much about these other methods, but in relation to other algorithms, they add the self-distillation and self-supervised label augmentation. Yes, thank you. It takes time, but I'll get the right ones eventually. So basically, we are adding the new method to different pre-existing methods and observe how much performance gain we get from each of them. Okay. That's it. And then I guess the last interesting part is looking at problems when we don't have a lot of training data, right? So, well, first, just limited data, and then they observe performance gain, for quite a big gain, 35% more. So motivated by that, they look at methods that lay in few-shot classification, which is basically means there is not much data, and there are, I think, two main approaches to solve the problem. One is find more data, things like data augmentation to create more data, but also tune your models. For example, tune the optimization method to find better solutions, right? So they apply the self-supervised label augmentation approach on these methods and observe performance gains. Let's look at the tables, which is, I don't see the table. Maybe there is no table. But they do mention that certain performance gains, 7%, for example, which is again relative percentage, right? Or in some cases is not that much, right? And the last related example problems is imbalanced classification. So this is when you have enough data for some classes, but not much for certain other classes. And again, by creating augmentations, we are actually generating data for those classes that don't have enough data points for training. And that's the performance results are in table 7, down on CIFAR 10 and CIFAR 100. And we can see sometimes quite significant performance gains, sometimes not that much compared to the baseline models, right? Any comments about experiments?
Yeah, I have a comment, or more rather like an open discussion, because I see that they've gone through a fair amount of trouble. So like they designed all these losses and all these training regimes, and when I see the performance gains, at least in my view, they are not as impressive to justify all the trouble of self-distillation, data augmentation, and redefining the losses and so on. So
I agree with that. I think I mentioned it earlier. So performance gains are not as impressive, but sometimes there is significant gain, right? But I think they are just trying to start a new research direction to do to use any of these techniques to improve performance, and that this might be like a really first paper to put all this together, and maybe we'll see better performances in upcoming papers.
yeah, I don't know, maybe someone else can pitch in about their experience with these methods, but it seems like they're really like, you know, like really getting all these marginal gains out of a lot of I mean, it is also true that they don't add that many more parameters to the model, so kind of makes sense. But I don't know, I see the other papers that we have seen where you get actually really impressive gains out of just changing the learning paradigm altogether.
Yeah, it depends maybe also because they might be already comparing against the best of the best. So it might just be harder to improve them. And it depends on if that is like a mission critical model also for some business, then that might very well worth it. This 1 or 2% improvement.
And Carlos,
yeah.
Oops, sorry, I couldn't comment on the other ones, but in the imbalanced regime, it really seems like if you're able to, essentially this kind of amounts to just generating synthetic examples. So instead of doing it in kind of a random way and then just retraining models until you figure out whether SMOT or some other randomly generated examples give you the best result, it's kind of baked in, so you'd only have to do it once. So that could be a benefit in that regime.
I also find it a bit surprising, or at least it was surprising to me at the moment, that when there is more data imbalance, they improve more than when there is less data imbalance. I mean, that could be just an artifact of the baseline being higher, but I think it's an interesting.
Oh, that is
Yeah, I mean, there is 34% accuracy, right? Which is not impressive at all. So maybe any improvement on that is is good because maybe it's just a very hard problem. Other comments about experiments? Okay, because they end the paper with a bit more intuition in related work, self-supervised learning, which is largely about the multitask learning we saw earlier with the sum of two loss functions. And then they also mentioned self-distillation, which is an extension from the distillation proposed by Hinton in 5 years ago. I guess that's all. If you have any more comments, anything I may have missed.
Cool. Are there any more questions from anyone in the attendees or comments? Okay, otherwise I'm going to stop the recording. Thank you very much, Vahan, for your time and for the paper.
Thank you very much.
And if we can give a show of hands to Vahan to show our appreciation, that would be great.
Thank you.